Hello everyone and welcome to Valiant Tech World. Today we're gonna talk about the math behind linear regression. We will start by summarizing a problem discussed in a previous video, and then we will show how to obtain the formulas used to solve a linear regression problem. The problem posed in the previous video was about an electric car that you just bought. You have used it to go around in your city, but now you are planning to do a long journey to another city. Given the long journey, you want to make sure that a fully charged battery is able to let you reach the other city so that you do not need to stop to a charging point. Hypothetically, you cannot find this information anywhere, so the only thing left to do is to collect data in order to make a prediction on the battery usage. So, you go around your city for your normal routine and start collecting the distance traveled and the related battery usage. For more info about the problem, go and check the previous video, which you can find in the description below. This problem can be posed as a linear regression, and let's briefly recap what a linear regression problem is. In this one-dimension example, you can see that you are trying to find a line which represents the data. In this case, there are two coefficients which we can call m and b. M modifies the slope of the line, while b is called the intercept, and it is the value of the output y when all the explanatory variables are equal to 0. In our problem, the only variable x is the distance traveled, while y is the associated battery usage. The main task in a linear regression problem is to find the coefficients which, in this case, are able to create a line where the difference between the data points and the created line is as small as possible. These differences are called residuals, and they need to be minimized. Going into the math, this problem can be solved by using a procedure called ordinary least squares, where the sum of all the squared residuals mentioned before are minimized. The first equation shows the linear equation of a single data point I, where it is added also an error term given that the data points do not precisely follow a linear equation, and the error term takes into account all the variation of the output which are not associated to the non-input variables. The second equation shows that in an ordinary least squares, the squared residuals are summed together for all data points, and by finding the optimal m and b coefficients, this final sum can be optimally minimized. You can see that the goal is to minimize the final sum of the squared differences between the observed value yi and the predicted values mxi and b. Note that m and b coefficients found are estimates, so we call them respectively m hat and b hat. However, for the rest of this discussion, I will simply call them m and b to simplify notation. In order to find these coefficients, we can do a derivative of this quadratic function and set it equal to 0. This is a common way of finding the minima and maxima of a function. For a quadratic function, like in this case, there is only a minimum or a maximum point. However, in this specific case, the function is also convex, so the derivative leads to the minimum point. Let's start with the intercept b. We can do the derivative with respect to b, remembering that the derivative of a quadratic function is 2 multiplied by the function multiplied by the derivative of the function. In this case, for a generic point I, looking at the orange text, you can see that the derivative of the terms within the brackets is simply minus 1, because y and mx do not have terms in b, and the derivative of minus b with respect to b is simply minus 1. Equation 1 shows that the derivative can be done for all the n points, and, given that they are not interacting with each other, all the derivatives can simply be summed together. Also, given that we set this function equal to 0, we can remove the multiplicative factor minus 2, because it is not going to change the point where the function is 0. Equation 2 shows that we can split the sum into 3 different terms. In particular, in the second term we can put m outside the sum, given that it does not depend on I. And the third term is simply the coefficient minus b, summed n times, so we can simply write minus nb. Equation 3 shows that if we put the first two terms on the other side of the equation and we divide by minus n, then we obtain an equation in B. In particular, B is equal to the sum of all the y values divided by n, which is the mean of the y terms, minus m multiplied by the mean of the x terms. We can calculate the mean of the x terms and y terms, so the only missing value is m. To find m, now we do the derivative with respect to m and set it to 0. In this case, looking at the orange text, you can see that the derivative of the terms within the brackets is minus xi, because y and b do not have terms in m, but the derivative of minus mxi with respect to m is minus xi. Equation 1 is similar to the previous case. We can again do the sum of all the derivatives and remove minus 2. Equation 2 shows that we can multiply xi for all the terms within the brackets, and then split the sums similarly to what we did before. In this case, note that the second term is a squared term, while the third term is not anymore minus nb, given that it is multiplied by xi, which depends on I. Equation 3 shows that we can replace the b value using the equation found before, and now this equation contains only terms in m, x and y. In equation 4, we move all the terms in m on the other side of the equation, while in equation 5 we divide for all the terms that are not m, and we can obtain a formula to find m, which only depends on the x and y data. This is what we are looking for, given that only by knowing the data points we can find the optimal m value. The formulas are a bit long, but we can simplify them. In particular, we can substitute the mean values of x and y respectively with x bar and y bar, and this simplifies the two equations for b and m. Also, another possible simplification is to create a deviation variable d, which is defined as the difference between a value x and its mean. In this way, the formula for m is more compact and readable. As shown in the previous video, the linear regression problem can also be defined for more than one independent variable, and the equations are typically written in a matrix form. For a generic point with output yi, then there are p different input variables and each of them is associated to a specific beta coefficient, and then there is also the coefficient beta 0, not associated to any particular variable because this is the intercept. Given that there are n data points, y is a vector of n by 1 dimensions, and also the error term epsilon is a vector of n by 1 dimensions. On the other hand, beta, as previously mentioned, is a vector of p plus 1 by 1 dimensions, where p is the number of input variables, and then we add the intercept. For the data, this is a matrix of n by p plus 1 dimensions, given that there are n data points, but for each data point there is a multiplication for the beta vector of coefficients, which is p plus 1 dimensions. You can see that in the matrix one column is all ones. That is the intercept column, which multiplies the beta 0 coefficient. This is a compact way to include the intercept in the input matrix, but the beta 0 does not multiply any other p inputs, given that every time it is only multiplied by 1. The ordinary least squares defined in matrix form is similar to the one-dimension case. The first equation shows how the problem is formally posed, and that is essentially the same equation used previously, where the sum of all the squared residuals is calculated and then minimized. But in this case the aim is to find a vector beta with all its p plus 1 coefficients. The two vertical bars at the left and right of the equation, as you can see from the orange text, mean that the Euclidean norm of the vector is calculated, which in the example is the square root of the sum of all the squared values of the t-vector. Also, This can be written as the multiplication between the vector t transpose and the original vector t. The Euclidean norm has the square root, but the function that we are trying to minimize is squared, so that we are simply considering the sum of the squared terms without the need of calculating the square root. The second equation shows, as mentioned before, that we can write the equation using the transpose and then we do the derivative and set it equal to 0. In this case, the derivative is in respect of a vector beta and not single variables as previously shown. The third equation focuses on performing the multiplications of the terms within the brackets by taking into account that the transpose of two matrices or a matrix and a vector are equal to the multiplication of the matrices or matrix and vector, both transposed, but they are flipped. If you look at all these four terms and apply matrix multiplications, you can see that dimensionally all of them are a single dimension, so that we are essentially obtaining a single value out of this, which is the error given a specific beta vector. Now let's do the derivative of these four terms by remembering some of the derivative identities in respect of a vector. In the orange text you can see that given two vectors a and x, the derivative of x transpose multiplying a and a transpose multiplying x in respect of x is a transpose. The other one to remember is that the derivative of x transpose ax in respect of x, where in this case A is a matrix, this is equal to 2x transpose A, where A should be a symmetric matrix. Now let's use these identities in equation 1. The first term does not have beta terms, so the derivative is 0. The second term is beta transpose which multiplies x transpose y, which together form a vector. So in this case the result is this vector transposed and we obtain y transpose x. The third term is similar to the second, but in this case is the vector transposed formed by y transpose and x, which multiplies beta. But the result is still the vector transposed y transpose x. The fourth term is beta transpose, which multiplies a symmetric matrix formed by x transpose x, which then multiplies beta. As shown in the orange text, this derivative is equal to 2 beta transposed and then the symmetric matrix, which in this case is x transpose x. The second equation shows that we can remove the first term and sum together the second and third term, which both are negative, and then the equation has only two terms. We can divide them both by 2 and then move the first term on the other side of the equation, and this leads to the third equation. From third equation we can transpose both sides, as you can see from equation 4. Remember that x transpose x is symmetric, so the transpose of this matrix has no effect and returns again x transpose x. Also, as you can see in the orange text, AB all transpose is equal to B transpose A transpose. This means that in equation 4 we can swap the beta transpose and x transpose x terms, and beta is not anymore transpose, while x transpose x remains the same. On the right hand of the equation, we can swap y transpose and x, and in this case, x becomes x transpose, and y transpose becomes y. You can see this in equation 5. Now, remembering that the inverse of matrix A, which multiplies A, is equal to the identity matrix, which is composed only by 1s on the diagonal and 0 everywhere else. The identity matrix behaves like the number 1 in a single dimension. If you multiply a number by 1, you get the same number. In the same way, if you have an identity matrix which multiplies a vector, you simply obtain the vector. So the last thing to do is to multiply both sides by the inverse of x transpose x. In this way, the left-hand side is the vector beta, while the right-hand side is composed by only terms in x and y, as you can see from the final equation at the bottom. This is a closed-form solution, which you can apply to obtain an estimate of the beta coefficients. This method assumes that we can do the inverse of the matrix. This is not always the case, but for now we can assume that we can compute it. By using the equation just shown, we can obtain the beta coefficients from the orange data points, and we can see that the estimates are close to the actual coefficients 3 and 0.4. They are not exactly the same values because the data points also have some error which is not considered in the linear equation. Given that the coefficients have been found by using this training data, now we want to use the same coefficients on a different set of data to understand if this line is a good representation of the data. Here again, the line is close to the data points, and the metrics root mean square error and R squared show that the line is a good fit for the data. There is a video on regression metrics which provides more details about them. You can find it in the description below. The blue point was the estimated point that we needed to find to understand if we could do a long journey without the need of recharging the battery. And you can see that the journey it would use around 80% of the battery. For more details about the electric car problem, there is a separate video which again you can find in the description below. That's all for today. If you enjoyed the math and found it useful, please click the like button and subscribe to this channel. Thank you for watching.